Welcome to the Deep Dive, where we extract the essential truth, the surprising backstory, and the lasting influence from history's most critical sources.
Today, we're tackling a figure who really just rebuilt our whole understanding of the cosmos.
That's right. Most people know him, for a falling apple.
Right.
But we're diving deep into the really complex, sometimes contradictory world of Sir Isaac Newton.
And we're going way beyond the standard school curriculum today. Isaac Newton was, and this isn't an exaggeration, pretty much the central figure in the history of science.
He wasn't just a physicist or a mathematician, was he?
No, not at all. He was this incredible polymath. His thinking stretched from inventing calculus and founding modern optics right through to, well, theology and even complex alchemy. Quite the range.
So our mission today is to unpack all of that. We want to look at the life, the, let's say, difficult personality, and the just world-altering impact of this unique figure. The genius, yes, but also the man behind it.
The fiercely competitive, secretive man.
Exactly. Understanding him, the person, seems key to understanding the achievements.
Well, to put his importance into context for you, you have to grasp the scale of what he did. His magnum opus, Philosophiae Naturalis Principia Mathematica.
Which everyone just calls the Principia.
Right, the Principia. Published in 1687, it established classical mechanics. It achieved the first great unification in physics, basically showing that the same rules govern things on Earth and things in the heavens. Celestial and terrestrial motion, all under one framework.
And that unification is really why he's held in such high regard. There's that famous epitaph by Voltaire, isn't there?
Oh yeah, sums it up perfectly. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light.
It almost makes him sound like a force of nature himself. Okay, let's start unpacking this massive legacy. Where better to begin than his, well, surprisingly tough and solitary early years?
So Isaac Newton. He begins life on Christmas Day, 1642, at Woolsthorpe Manor in Lincolnshire. That's using the old-style calendar they had back then in England.
And right from the start, things weren't easy.
No, not at all. He was born prematurely. His mother, Hannah Eiskopf, apparently said later that he was so tiny at birth he could, and this is literal, have fit inside a quart mug.
Wow. A fragile beginning.
Physically fragile, yes. And the family situation just added to it. His father, also Isaac Newton, was a farmer, reasonably well off, but he died 3 months before Isaac was even born.
So born fatherless.
Yeah.
But the real disruption came a few years later.
That's right. When Isaac was just 3, his mother remarried. Her new husband was a wealthy, older clergyman, Reverend Barnabas Smith.
Okay.
And she moved away to live with Reverend Smith, leaving young Isaac behind. He was raised by his maternal grandmother.
Left behind. That must have been incredibly difficult for a 3-year-old.
You have to think it caused deep, lasting psychological scars. This sense of abandonment perceived by a small child. It seems to echo through his later life.
Yeah, we don't actually have to speculate too much about the emotional fallout, do we? There's that rather chilling document.
The list of sins. Yeah. He compiled this list himself before he turned 19. It's this fascinating mix of intense self-scrutiny and, well, guilt.
And on that list, there's one entry that just stops you in your tracks. It reveals the depth of that early anger.
It really does. He confessed to threatening my father and mother Smith to burn them and the house over them.
Threatening to burn them and the house over them. That's intense.
It shows a profound level of, repressed violent anger.
Yeah.
Directed right at his mother and stepfather.
We should maybe pause on that. This wasn't just a kid having a bad day. This is the future architect of our rational universe, documenting this desire for murderous arson against his family. It really suggests that the immense control and discipline we see later in his scientific work might have been, well, a necessary coping mechanism, containing something powerful and volatile inside.
It's highly plausible. You see hints of it later, the solitary nature, the absolute drive for control, the fierce competitiveness. It all seems potentially rooted in that traumatic, abandoned childhood. His need for certainty, absolute certainty, maybe it starts there. #type education at Cambridge.
Okay, so despite this turbulent start, he did manage to get a formal education. The King's School in Grantham.
Yes, that gave him a solid foundation. Mathematics, Latin, Greek, the standard stuff, but crucial, though his path almost took a very different turn.
The farming detour.
Exactly. His mother was widowed again, brought him back home to Woolsthorpe, and she tried to make him a farmer, manage the estate.
How'd that go?
He hated it, absolutely despised it. The stories say he was usually found hiding somewhere reading a book when he was supposed to be, watching sheep or fixing fences.
Thankfully, someone saw his potential.
His uncle, yeah, and the schoolmaster from Grantham, they basically tag-teamed his mother, persuaded her that this boy was not cut out for farming and needed to go back to school, and eventually on to university.
So Cambridge, Trinity College in 1661.
But not as a privileged student. He entered as a subsizar.
What does that mean exactly?
It means he had to work his way through. He essentially acted as a valet, a servant to the wealthier students to cover his fees.
That must have reinforced that feeling of being an outsider.
You'd think so. But he buckled down, worked incredibly hard, and earned a proper scholarship in 1664.
And he wasn't just sticking to the old curriculum. He was diving into the new stuff.
Absolutely. He went way beyond Aristotle. He started engaging deeply with the modern thinkers, the mechanical philosophers, Descartes, Galileo, people like that.
And that led to his famous notebooks.
The questions.
Yeah.
Yes. Latin for questions. He started filling these notebooks, questioning the established ideas, developing his own thoughts on this new mechanical philosophy. It's fascinating to see his mind at work even then.
And all this intense, solitary study pays off incredibly quickly. He becomes the Lucasian professor of mathematics at Cambridge.
At the age of 26. It's extraordinary. He succeeded his own mentor, Isaac Barrow.
But there was a potential roadblock there, wasn't there? Something about religious requirements.
A huge one, yeah. Fellows at Cambridge, especially someone in a position like the Lucasian chair, were generally required to take holy orders in the Anglican Church, become ordained.
And Newton had issues with that.
Big issues. Privately, he held some pretty radical religious views. He rejected the doctrine of the Trinity. Some scholars basically label him a heretic, an Arian.
So taking holy orders would have meant publicly affirming beliefs he didn't actually hold.
Exactly, a massive crisis of conscience. Or, potentially, the end of his academic career if he refused. So what does he do?
He pulls strings.
He secures a royal dispensation from King Charles II himself. It specifically exempted the Lucasian professor from the ordination requirement. He basically navigated the political system to protect his position and his private beliefs. Quite shrewd. #tag personality traits and early interests.
When people try to sum up his character, that term Janushan thinker often comes up. What does that really capture about him?
It captures his immense versatility. Janus, the Roman god, had two faces looking backward and forward. Newton did that intellectually. He could draw on ancient thought, classical geometry, but apply it to create entirely new, forward-looking science. He combined disparate fields in really creative ways.
And underpinning all that was just incredible discipline.
Oh, absolutely. A prodigious appetite for work. He'd work through the night, apparently forget to eat, prioritize his studies over his health, everything. Later in life, he became a vegetarian, lived quite an ascetic lifestyle. It all points to intense focus and self-control.
He sounds very controlled, maybe isolated. The sources describe him as secretive, neurotic.
Fiercely competitive, definitely. And we know he never married.
Right. Voltaire famously claimed Newton was never sensible to any passion, nor had any commerce with women.
It seems his life was just singularly devoted to the intellectual quest. Even his hobbies, before the big physics breakthroughs, show this practical, precise mindset. He wasn't just daydreaming. He was building complex sundials, intricate models of windmills, real engineering alongside the abstract thinking.
He even tried to create a universal language, didn't he? Trying to impose rational order on everything.
Yeah, that pursuit of order, of underlying rules, seems fundamental to him.
So this intense, controlled, incredibly disciplined mind is then suddenly forced into total isolation. And that isolation leads to, well, perhaps the biggest breakthrough period in scientific history.
Right, 1665, disaster strikes London, the Great Plague. Cambridge University shuts down as a precaution.
So Newton, having just got his BA degree, heads back home to Woolsthorpe Manor.
And he stays there, essentially in quarantine for the better part of 2 years.
It's just amazing to think about. This period of enforced isolation, it's universally seen as, the richest and most productive ever experienced by a scientist.
It's staggering, really. In that short span, basically hiding out at home, Newton develops the fundamental principles of calculus.
His fluxions.
His fluxions, yeah. He formalizes his groundbreaking theories on light and optics, and, crucially, he lays the groundwork for his theory of universal gravitation.
All at once.
Pretty much simultaneously. An explosion of creativity across mathematics, physics, optics. It's unparalleled.
And the most iconic image of the entire scientific revolution comes from that time, from that garden at Woolsthorpe. The apple. Let's set the record straight on the apple story.
Okay, the story is essentially true, but no, it didn't hit him on the head. That's the myth.
So what did happen?
Newton himself recounted it later to people like William Stukeley and his niece's husband, John Conduit. He described being in the garden, contemplating and seeing an apple fall from a tree, straight down.
And the big idea wasn't, oh, look, things fall down. Obviously.
Obviously not. The leap was conceptual. He started thinking, why does the apple fall straight down? Why does that force, gravity, only act near the Earth? Why shouldn't it extend further out, much further?
Maybe as far as the moon.
Exactly. Could the same force pulling the apple be the force holding the moon in its orbit around the Earth? He started doing the calculations, comparing the rate the apple falls to how much the moon falls towards Earth in its orbit. And he realized the force was likely the same, just diminishing with distance, specifically diminishing with the square of the distance. That simple observation, thinking about why the apple fell vertically, became the key that unlocked the mechanics of the entire solar system. #tag development of calculus.
Okay, so to actually calculate all this gravitational stuff properly, he needed new mathematical tools to describe things that are constantly changing.
Which led him to calculus, or as he called it, the method of fluxions.
And he started working on this incredibly early, right?
Yeah.
Back in 1664.
Even before the plague years fully kicked in. By mid-1665, he'd figured out the essential techniques, how to find tangents, calculate areas under curves, the core of calculus. He definitely developed it first.
But then came the infamous fight with Leibniz. Gottfried Wilhelm Leibniz, the German mathematician.
Ah, yes, the great calculus war. Decades of bitterness. Leibniz independently developed calculus around the same time.
And crucially, Leibniz published first.
Yeah.
And his notation, the symbols he used.
They were just better, more convenient, easier to use. The DDX notation, the integral sign that's mostly Leibniz. And mathematicians on the continent adopted Leibniz's system much more readily.
Which led to this huge priority dispute. Who invented it first?
And it got ugly, really ugly. Newton, later as president of the Royal Society, basically used his power to stack the deck. He oversaw the committee investigating the dispute.
And essentially wrote the concluding report himself.
Pretty much. The report declared Newton the sole discoverer and basically branded Leibniz a fraud, a plagiarist. It poisoned relations between British and continental scientists for years. Shows you that fierce, competitive, perhaps ruthless side of Newton again.
It seems so contradictory to the spirit of scientific inquiry. But despite that, later mathematicians, people like Penrose and Arnold, still admired Newton's original mathematical methods in the Principia. Why was that?
Because Newton, in the Principia, didn't present calculus using his fluxional notation or even algebraic methods primarily. He used geometry. Classical Euclidean-style geometry, pushed to its limits with concepts of vanishing quantities, what he called the method of first and last ratios.
That was geometrical calculus.
In essence, yes. And for mathematicians who appreciate that kind of thinking, it felt more rigorous, more elegant. It seemed to reveal the underlying physical principles in the geometry itself, not just through symbolic manipulation. Plus, beyond calculus, Newton also generalized the binomial theorem and did pioneering work in what we'd now call vector analysis, like adding forces using parallelograms. His mathematical toolkit was just immense. #tag optics and the nature of light.
Okay, so while he's inventing calculus, he's also revolutionizing the understanding of light. Those prism experiments in 1666.
Right. Everyone knew prisms made rainbows. But Newton did it systematically. He passed a beam of sunlight through a prism and noted that the spectrum of colors that came out wasn't circular like the incoming beam, but oblong, stretched out.
Why was that significant?
It showed that the different colors must be bending or refracting by different amounts as they went through the glass. Blue light bent more than red light, for instance.
And the big conclusion from that
was that color isn't something the prism adds to the light. Color is intrinsic to the light itself. White sunlight is actually a mixture, a composite, of all the different colors of the spectrum, and the prism just separates them out. A radical idea for the time.
And this understanding of how light bends had immediate practical consequences for telescopes.
Yes, he realized that telescopes using lenses refracting telescopes would always suffer from this effect. Because different colors focus at slightly different points, you get blurry images with colored fringes around the edges, chromatic aberration.
An unavoidable flaw in lens-based telescopes. So Newton, the great theoretician, decides to solve this engineering problem himself.
Exactly. If lenses cause the problem because light passes through them and bends, why not use a mirror instead? Reflection doesn't separate colors in the same way, so he built the first practical reflecting telescope.
The Newtonian telescope.
That's the one. He had to figure out how to grind the mirror perfectly from a special metal alloy called speculum, make it highly reflective. But it worked. It produced clearer images without the color distortion, paving the way for much larger and more powerful telescopes. A massive technological leap.
And even on the fundamental nature of light itself, he was ahead of the curve, wasn't he? He mostly favored a particle theory.
The corpuscular theory, yes. Light as tiny particles. But he wasn't dogmatic about it. He also observed phenomena that seemed more wave-like.
Like what?
Like the interference patterns you see, the colorful rings, Newton's rings when light reflects between two surfaces close together. He struggled to explain these purely with particles.
So he was already grappling with this duality.
He was the first to seriously try and reconcile particle-like and wave-like properties. He didn't have the full picture, of course, that required quantum mechanics centuries later, but he saw that light was more complex than just simple particles or simple waves. Some people even call him the first quantum physicist, in a way, for recognizing that tension.
So Newton has calculus, optics, the foundations of gravity, all worked out basically during those plague years. But it takes quite a while for the big book, the Principia, to actually appear. What prompted him to finally publish?
Well, he kind of put celestial mechanics aside for a while, but then around 1679, a couple of things happened. A prominent comet appeared, which got astronomers thinking. And he had some correspondence, some debate actually, with Robert Hooke about the forces governing planetary motion.
Ah, Hooke again, his rival.
That exchange seems to have spurred Newton to really nail down the mathematical proof. He showed conclusively that if you have a force pulling toward a central point, and that force decreases with the square of the distance, then the planets must move in ellipses, just as Kepler had observed.
He cracked it.
He cracked it. He wrote up a short version of this proof in a tract called De Motu Corporum in Gyrum, on the motion of bodies in orbit.
And this is where Edmund Halley comes in.
Crucially, yes. Halley, the astronomer famous for the comet, saw this short paper and immediately grasped its immense significance. He went to Cambridge, talked to Newton, and urged him to publish the full theory.
He didn't just urge him, though, did he?
No, he did much more. The Royal Society was supposed to pay for the printing, but they were basically broke at the time. So Halley paid for the publication of Philosophia Naturalis Principia Mathematica out of his own pocket.
Wow. Halley essentially bankrolled the single most important scientific book ever written.
You could say that, yeah. Without Halley's push and his financial backing, the Principia might never have seen the light of day, or at least not in the form it did.
And writing it took a huge toll on Newton himself.
Oh, absolutely. The sheer mental exertion was enormous. We have accounts, like from his biographer, saying that trying to work out the complex details of the moon's motion, which is affected by both the Earth and the sun, literally made his head ache and kept him awake so often that he would think of it no more.
He pushed himself to the absolute limit.
Yeah.
Hashtag tag the three laws of motion explained.
So, the Principia lands in 1687. At its heart are the three famous laws of motion.
The bedrock of classical physics.
Absolutely. Law 1, inertia. An object stays at rest or moves at a constant velocity unless a force acts on it. Law 2, ephemer. Force equals mass times acceleration. The harder you push, or the less massive the object, the faster it accelerates. Law 3, action-reaction. For every action, there's an equal and opposite reaction.
Simple statements, but they unified everything.
Everything from, a falling apple to the orbit of Jupiter. It was the first great unification in physics, showing the same basic laws apply everywhere. These laws absolutely dominated science for over 2 centuries, and they were fundamental to the Industrial Revolution.
Now, the Principia itself is famously difficult to read. Written in Latin, using that geometrical style of calculus.
Very dense. Not exactly a beach read.
But it contained more than just the three laws and the theory of gravity, right? What else was packed in there?
Oh, a lot. For example, he included the first proper theoretical calculation of the speed of sound in air. He predicted that the Earth should be slightly flattened at the poles due to its rotation and oblate spheroid.
Which was a direct challenge to other theories at the time.
Yes, particularly the vortex theories of Descartes, which predicted the opposite, an elongated Earth. Newton was proving his system superior by making testable predictions. He also had detailed analysis of fluid resistance, tides, comet paths, and even a description of an experimental setup using falling objects in a controlled airflow. Basically an early concept of a wind tunnel. It's just packed with insights, hashtag universal gravitation and its impact. And then the crowning achievement, the law of universal gravitation.
He used the Latin word gravitas, right? Meaning weight, or heaviness.
Yes. And he proposed that this gravitas wasn't just an earthly phenomenon. Every single particle of matter in the universe attracts every other particle,
With a force that depends on their masses.
directly proportional to the product of their masses. More mass, more pull.
And inversely, proportional to the square the distance between them.
Exactly. Double the distance, the force drops to a quarter. Triple the distance, it's down to a ninth. This precise mathematical relationship was the key.
And the power of this law was that it immediately explained so much.
Everything fell into place. Kepler's laws of planetary motion weren't just observations anymore. They were derived consequences of gravity. The tides could be explained by the gravitational pull of the moon and sun. Comets, previously mysterious wanderers, now had predictable paths. Even the slow wobble of the Earth's axis, the precession of the equinoxes, could be calculated using his law.
It basically settled the debate about the solar system being heliocentric, centered on the sun.
Absolutely. The sheer explanatory power was overwhelming, but it wasn't without controversy.
People weren't comfortable with this invisible force acting across empty space.
No. Critics immediately asked, how does it work? What is gravity? How can the sun possibly pull on the Earth with nothing in between? They accused him of bringing occult agencies, hidden forces, back into science, which the mechanical philosophers had tried to banish.
And Newton's response to this criticism became incredibly famous.
Yes. In the second edition of the Principia, facing these demands for an explanation of gravity's cause, he added that famous statement,
Hypotheses non fingo.
I frame no hypotheses, or I feign no hypotheses. His point was, look, my job as a scientist is to observe, measure, and find the mathematical laws that describe how things happen. The law of gravity describes the how perfectly. As for the why, the underlying cause. If I can't deduce it from experiments or observations, I'm not going to speculate.
So stick to the observable facts and the math that describes them. Don't invent explanations you can't prove.
Precisely. It was a powerful statement about the limits and rigor of the scientific method. Describe what you can measure and calculate and leave untestable speculation aside. This became a cornerstone of empirical science.
That same rigor didn't always extend to his personal interactions, though. For someone so focused on objective truth, he could be incredibly political and, well, prickly and challenged. #tag rivalries with Hooke and Leibniz.
Oh, absolutely. We mentioned the calculus feud with Leibniz. That dragged on for decades, right up until Leibniz died. Newton really used his position, especially as president of the Royal Society, to manage the narrative, ensuring he came out looking like the original discoverer and Leibniz the fraud. It wasn't his finest hour, ethically speaking.
Yeah, and then there's Robert Hooke again, that famous quote. If I have seen further, it is by standing on the shoulders of giants, often presented as humility.
It sounds like humility, acknowledging his debt to predecessors like Galileo or Kepler. And maybe partly it was, but given his intense rivalry with Hooke,
There might be a hidden jab.
many historians think so. Hooke was known to be a man of short stature, possibly with some curvature of the spine. The shoulders of giants phrase was actually an existing saying, often phrased as a dwarf on a giant's shoulder sees farther of the two.
Ah, so if Newton's the one seeing further,
The implication could be that Hooke is the dwarf he's standing on. It's possibly a very subtle, very pointed insult disguised as modesty. Typical Newton, perhaps complex, maybe calculating even in his compliments.
who really held grudges, didn't he?
Yeah.
Any other major scientific feuds?
John Flamsteed, the first astronomer royal. Newton desperately needed Flamsteed's highly accurate star charts and planetary position data for refining his theories, especially for the second edition of the Principia.
And Flamsteed wouldn't share.
But Flamsteed was meticulous, maybe overly so. He considered his data not quite ready for publication, still needed checking. Newton got impatient. Using his influence at the Royal Society, he essentially forced the publication of Flamsteed's catalog prematurely under Halley's editorship without Flamsteed's final approval.
Flamsteed must have been furious.
Livid, it completely destroyed their relationship. Flamsteed managed to track down and burn most of the copies of that unauthorized edition. Another example of Newton prioritizing his own scientific needs over personal relationships or scientific courtesy. #tag Newton as president of the Royal Society.
Okay, so despite these conflicts, or maybe because he was effective at wielding power, his position in the scientific establishment became supreme.
Totally. Lucasian professor at 26, fellow of the Royal Society fairly early on, and then, from 1703 until he died in 1727, he was president of the Royal Society, over 2 decades in charge.
A dominant figure. But there's that strange contradiction. The greatest scientific mind, but apparently a terrible teacher.
utterly ineffective by all accounts. His assistant, Humphrey Newton, no relation, recorded that Newton's lectures at Cambridge were often delivered to an empty room.
Literally no student showed up.
Apparently, and if the room was empty after about half an hour, Newton would just deliver the rest of the lecture to the walls, as the account goes, and then head straight back to his lab and his experiments.
He fulfilled the obligation, but had zero interest in actual teaching?
Seems that way. His focus was entirely on his own research, not communicating it to students. He was also knighted, wasn't he, Sir Isaac Newton?
Yes, Queen Anne knighted him in 1705 during a visit to Cambridge.
But the timing suggests it wasn't purely for his science. It seems to have been more connected to the upcoming parliamentary election, where Newton was involved in university politics. A politically motivated honor, perhaps, more than a scientific one at that specific moment. ### his role at the Royal Mint.
All right, now for maybe the most surprising chapter of his life. The world's greatest physicist spends his later years running the Royal Mint.
It seems counterintuitive, doesn't it? In 1696, he moved to London to become Warden of the Mint. Later, from 1699 until his death, he was Master of the Mint.
Weren't these often just ceremonial posts,
Right.
cushy jobs?
Often, yes. Sinecures. But Newton wasn't like that. He took the job incredibly seriously, applying the same obsessive focus he brought to physics. And he arrived at a time of crisis, the Great Recoinage of 1696.
What was the problem?
Counterfeiting was rampant, especially coin clippings shaving tiny bits of silver off the edges of coins. It was estimated that maybe 20% of the coins in circulation were fake or underweight. It was destabilizing the entire economy.
And clipping was a serious crime.
High treason, punishable by hanging, drawing, and quartering. Newton essentially became a detective and prosecutor.
Seriously. The man who discovered gravity went undercover.
Well, maybe not quite undercover in a trench coat, but the accounts say he personally gathered evidence, interviewed informants, sometimes in disguise, frequenting shady bars and taverns in the London underworld to track down counterfeiters.
That's incredible.
He conducted over 100 cross-examinations of witnesses and suspects. He was relentless. He brought his analytical mind to bear on criminal networks.
Did he have much success?
Remarkable success. He successfully prosecuted 28 coiners. The most famous was William Challoner, a really audacious master counterfeiter who'd even accused Newton himself of incompetence. Newton meticulously built the case against him, and Challoner ended up being hanged, drawn, and quartered. Newton showed no mercy to those who corrupted the system.
So he brought order to the currency, just like he brought order to the cosmos.
In a way, yes, and not just by catching criminals. He applied his scientific mind to the minting process itself. He improved the technology, the quality control.
Made the coins more accurate.
Dramatically, he significantly reduced the variation in the weight of newly minted coins, especially the gold guineas. This physical precision helped restore public trust in the currency.
And he influenced economic policy, too.
He did. His report in 1717, setting the relative value of gold and silver, effectively put Britain onto a de facto gold standard, moving away from bimetallism. He also had quite modern views on finance, understanding that paper credit and government debt could actually stimulate trade, and that ultimately currency value depended on public confidence, a very practical application of his intellect in his later years.
So looking back at the entirety of his work, how do we measure his impact?
Well, other great minds have tried. Lagrange, the brilliant mathematician, flat out called Newton the greatest genius who ever lived. And most historians would agree he's arguably the single most influential figure in the history of Western science.
And the Principia stands as the monument to that.
Absolutely. Stephen Hawking called it probably the most important single work ever published in the physical sciences. Ludwig Boltzmann, another giant of physics, said it was the first and greatest work ever written about theoretical physics. High praise from people who knew what they were talking about.
It wasn't just the results, though, was it? It was also how he did science.
Exactly. He didn't just give answers, he defined the process. He laid out rules for scientific reasoning in the Principia. Things like, don't invent unnecessary explanations, admit no more causes than are both true and sufficient. And what you learn from experiments can be generalized. Propositions inferred by general induction should be looked upon as accurately or very nearly true.
So observation, experimentation, mathematical description, careful generalization.
And meticulous record-keeping, replication. It's the foundation of the modern scientific method.
What's truly astounding is that he seemed to excel at everything: theory, math, experiments.
He really is in a class by himself in that regard. You can compare him to Archimedes or Gauss as a mathematician, maybe the top three of all time, but neither of them combine that with his level of revolutionary theoretical physics and his practical, experimental, even engineering skill. He was the complete package. #, his place in the Enlightenment.
And the impact went way beyond science labs, didn't it? His work is often seen as the starting gun for the Enlightenment.
Definitely. The Principia's publication is a major marker. Newton showed that the universe wasn't some chaotic, mysterious place governed by divine whim, but an orderly system operating according to rational, discoverable, natural laws that human reason could figure out.
That idea, a rational, predictable universe, was revolutionary.
It was the essential seed for Enlightenment thinking. If the cosmos operated on natural laws, maybe society should too.
So philosophers took his model and applied it to human affairs.
Thinkers like John Locke, Voltaire, Montesquieu, they explicitly drew on this Newtonian concept of natural law. They argued for natural rights, rational government, systems based on reason rather than just tradition or divine right. Newton's clockwork universe provided the model for a rational, ordered society.
But again, we have to confront the paradox. The father of Enlightenment rationality was also deeply involved in things that seem, well, not so rational.
The other side of the Janus face, yes. We can't ignore that the supremely rational scientist was also a profoundly religious man, though in an unorthodox way. He spent an enormous amount of time on theology, biblical interpretation, complex chronologies trying to date biblical events precisely. More than half his known writings are on these subjects, not science.
Trying to find the rational order in Scripture, too.
Perhaps trying to decode God's plan as revealed in the Bible, just as he decoded God's plan in nature.
And then there's the alchemy, or chemistry, as it was known.
A huge part of his private work. It's estimated he wrote something like 1 million words on alchemy, kept mostly secret, unpublished.
John Maynard Keynes famously called him the last of the magicians, right? Not the first modern scientist, but the last of an older tradition.
Keynes argued Newton believed the universe held deep secrets, codes that could only be deciphered by initiates, through ancient wisdom found in alchemy and scripture, as well as through mathematics and experiment. He saw it all as connected different paths to understanding the divine architecture of the world.
It seems contradictory hypotheses non fingo on one hand, trying to transmute metals on the other.
It does. But you could also argue that the meticulousness required in alchemy, the careful heating, weighing, observing tiny changes, keeping detailed secret notebooks, actually honed the experimental discipline he used in his physics and optics. The skills might have transferred, even if the goals were different. It was all part of his obsessive quest for hidden truths. #, how his ideas shaped the modern world.
Okay, so we've placed him among the giants. How do his specific ideas echo in the world we live in today?
Well, fundamentally, classical mechanics, the physics he established, is still the basis for almost all everyday engineering and technology. Buildings, bridges, cars, airplanes, they all operate according to Newtonian principles.
The Industrial Revolution wouldn't have happened without him.
It's hard to imagine how it could have. You need that understanding of forces, motion, energy, even space flight, while needing Einstein's relativity for extreme precision, relies heavily on Newtonian mechanics for trajectories and orbits.
And Einstein himself held Newton in incredibly high regard.
Immense regard. Einstein apparently kept pictures of Newton, Faraday, and Maxwell on his study wall. He said that Newton's achievement creating calculus and the laws of motion was perhaps the greatest advance in thought that a single individual was ever privileged to make.
Even though Einstein's own theories ultimately superseded Newton's in certain domains.
Yes, but relativity builds upon Newton. It doesn't completely discard him. It shows the limits of the Newtonian framework, mostly at very high speeds or in very strong gravitational fields. For most practical purposes, Newton's laws are still incredibly accurate.
His legacy is literally woven into the fabric of science.
Down to the units we use. The Newton is the standard international unit of force. And think about his burial. The first scientist ever to be buried in Westminster Abbey alongside kings and queens. That's a powerful statement about the cultural shift he represented. His birthplace, Woolsthorpe Manor, is now a tourist site, a place of pilgrimage almost. #outro.
It really is an extraordinary story. You start with this tiny, premature, seemingly abandoned boy.
Who becomes the dominant intellectual figure of his age, maybe of any age.
The Lucasian professor who couldn't be bothered to teach students. The revolutionary philosopher who engaged in bitter personal feuds.
the rigorous mathematician who moonlighted as a crime-fighting master of the mint.
And the ultimate rationalist scientist who spent maybe half his working life as, yes, perhaps the last magician, immersed in alchemy and theology.
That tension is what makes him endlessly fascinating. The public face of the cool, detached, mechanical philosopher versus the private man wrestling with ancient texts, secret codes, and unorthodox religious beliefs. He was utterly consumed by the need to understand how everything worked, on every level.
And he seemed acutely aware, even with all his success, of how much remained unknown.
That's maybe the most profound thing about him. That famous quote reportedly said near the end of his life, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore."
And diverting myself in now and then, finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me.
Just beautiful. A statement of incredible humility from arguably the most successful scientist who ever lived.
So thinking about that vast ocean of truth still undiscovered, and considering Newton's own dedication to those hidden unpublished studies and his refusal to frame hypotheses about gravity's cause, it makes you wonder, what fundamental forces or principles are operating in our world right now that we, like Newton with gravity, can observe, calculate, even manipulate? But whose underlying nature we still don't grasp? What are we refusing to hypothesize about because it seems too strange, too occult?
What vast oceans of truth are still lying right in front of us, waiting for someone with the insight or perhaps the courage to see the connections?
A challenging thought for all of us.
Indeed. Well, thank you for joining us on this deep dive into the colossal, complex life and legacy of Sir Isaac Newton.
If this exploration surprised you or made you think, please share it with someone else who loves history and big ideas. Keep exploring that ocean of truth. We'll see you next time on The Deep Dive.